the same way that we talked about the equilibrium for weak acids, now we talk about the weak bases. This is another useful equation that you need to keep in mind for any types of bases. You can just be standing for a base and base plus water, always acid plus water or base plus water. Base is going to accept the proton and become BH with a positive charge, and the water is going to act as acid, so it's going to lose its hydrogen and change to OH with a negative charge. And then instead of Ka, now you're dealing with the bases, so you write Kb. The same way the products over the reactants, their molar concentration, and still water is not a part of the equilibrium. The example is ammonia. Ammonia is a good base. When it acts as a base, it needs to accept one proton, right? So instead of 3 hydrogens, it will have 4 hydrogens with a positive charge, and OH will remain. So that's how you write the equation, and of course you will write the liquid, and the rest of them are aqueous. So some base ionization constants are given. If you need to work with any of these constants, the constants will be given. You don't need to be worried about memorization of anything. You have some more examples about writing the Kb of the reactions, like for example ethylamine. Again, these are organic compounds. Don't worry about their names or their structures. You will learn them in those of you who need to take organic chemistry. So what would you have if this is the base? Then you will have, instead of, and the hydrogens that you use, they're accepted, they will be connected to nitrogen. So C6H5, how many more hydrogens will be added? 1 more. So instead of 2 hydrogens, you have 3 hydrogens. And because it's a proton with a positive charge, so you will have a positive charge there, plus OH. So that's the same thing for every other example you have that you can work on them. Now we have different parameters for our calculations, Kb, pH, pOH. So let's start working on one of them on slide number 40. What does it say? It says aniline C6H5 in H. Let me call it B, base, minus water will change to EH plus OH. Okay? Aniline is used in manufacture of some perfumes. What is the pH of? So we are solving for pH of a 0.035 molar of aniline at 25 degrees Celsius. Kb is given 4.2 times 10 to negative 10 at 25 degrees Celsius. So whenever you have pH, it should remind you of concentration of hydrogen ion. But do you see any hydrogen ion here? No. Instead you have OH, and you know that you can find concentration of hydrogen ion, hydronium ion from OH, or pH from POH. So let's build our ice table. 0, 0. Minus x plus x plus x. Equilibrium we have. I skip the calculations that you already have. So Kb, which is 4.2 times 10 to negative 10, is x squared divided by 0.035 minus x. Alright, so the original value 0.035. Wait a minute, is it 0.2 or 0.05? 0.035 divided by 4.2 times. There is a typo on the PowerPoint slides. It's definitely more than 1,000. So your assumption is valid, and when you calculate X, which is concentration of OH, and you just need the OH because you need to have the pH, don't bother yourself with the rest of them. X is going to be 9.2 times 10 to negative 6 molar. Now you have two choices. You can find POH first or find the concentration of hydronium ion first. Finding POH, in my opinion, is easier. So POH is minus log of 9.2 times 10 to negative 6, which is 5.04. And then what was the relation between pH and POH? pH plus POH is 14. So pH is 14 minus 5.04, which is equal to 8.96. And this is a basic solution. The pH is above 7, and it makes sense, absolutely makes sense. So everything is the same for bases and acids. Instead of Ka, you're dealing with Kb, and instead of acidic strength, you're talking about basic strength. But the procedure is exactly same. The next part. Whenever you add an acid and a base, like HCl plus NaOH, you remember you had from Chem 1, you had a double displacement reaction between acid and base. So H and OH combined and Na and Cl. From school days, they told us that the product of addition of acid and base will give us salt and pepper, huh? I'm kidding. Salt and water. So here it's table salt, but in chemistry, any ionic compound is called salt. Ionic compound is called salt. Now we are going backwards and talking about this salt to find out if we dissolve some of these salts in water, if they make the solution acidic, basic, or they remain neutral. Ready? Now, starting with the cation of a strong base. This is a cation of a strong base, right? NaOH is a strong base. And for a strong base, when you had NaOH, what did we say? You remember I drew the irreversible reaction arrow, and I said it's going to completely ionize, right? Because it's a strong. If a base is a strong, again from last chapter, if a base is a strong, its cation is weak. So this cation, sodium cation, is so weak that when you add it, the ion, when you add it to water, nothing is going to happen, because by adding NaOH to water, everything will ionize to Na and OH. But Na is so weak that cannot form anything. So it will remain neutral. The water, the solution remain neutral. On the other side, if you talk about an anion like chloride, and you add it to H2O, it's an anion of a strong acid. It comes from HCl, right? We said HCl, when it's added to water, it fully ionizes 100% to H and Cl. So again, this is so weak that cannot do anything. And when you add it to water, no reaction. Again, the solution remains neutral. But the conjugate acid of a weak base or the conjugate base of a weak acid, they will make changes. For example, NH4 plus water. We always add them to water, okay? The second component is always water because this is the solution in water. So, if this is the conjugate acid of a weak base, if this is going to be the acid, it's going to give its proton, right? Correct? So, this is for acid, so it makes it acidic. Fluoride, so this comes from NH4OH, right? This is the conjugate acid of a weak base, we said. F, you combine it with H. What type of acid is it? It's a weak acid. Remember, we talked about the last chapter. If you add it to water, and don't forget the second component is always water, then you will have HF plus OH. What is released in the solution? OH, so it makes the solution basic. Now, the method that I teach you here for finding the effect of salts on the solution is a little bit different from what you see in the PowerPoint slides, but I guess it's more understandable. So whenever you see the salt, I want you to divide it to cation and anion, right? This cation comes first and anion comes second from CHEM-1. Now, you add the cation to OH, so it will form NaOH, right? You add H to anion, or you dissolve them in water, they will form these. Tell me, is NaOH weak or strong? NaOH, everybody knows, is a strong base. HBr, is it a strong acid or a weak acid? We talked about it is a strong acid. So a strong acid and a strong base can neutralize each other and the solution remains neutral. Or the way that your PowerPoint slide is explaining is that Na is the cation of a strong base, so it does not react with water, the same thing that I told you. And bromide is the conjugate base of a strong acid, so again it does not react. Or you can go with my way. Any of them will go to the same results. NaC2H3O2. Change it, divide it to cation and anion. I'm sure you will say this is your cation. Combine it with OH. It will form NaOH. And C2H3O2, it's the anion. Combine it with hydrogen. So it's going to be HC2H3O2, that's vinegar. Is it on the list of your strong acids? No, this is a strong base, but this is a weak acid. So between a weak and a strong, which one wins? The strong one, right? So the solution gets the property of the strong one. So the solution is going to be basic. Or you can say this doesn't react, but conjugate base of a weak acid reacts to form a base, whichever, again, easier for you. NH4Cl is the next example. NH4Cl divided NH4 plus Cl negative. NH4OH, we said we add OH and H here. Is NH4OH strong or weak? It's weak. And now you might ask, how do you know this is a strong or weak? If you go back to your book, you had it in Chem 1 when we talk about acids and bases. You had the Bromstead and Lowry. Go and check the list of strong acids and strong bases. You have 6 strong acids and 6 strong bases. If I'm not wrong, but please check it with your book again. 6 strong acids are HClO4, H2SO4, HNO3, and then HBr, HCl, and HI. Strong bases, NaOH, CaOH2, SR, lithium. Okay, let's NaOH, KOH, CaOH2, and 1 or 2 more. I'm not sure if it is LiOH and maybe magnesium OH. I'm not sure. Please check these. But anything is not on this list that you memorize, it's not difficult to memorize them, then they will be weak. So HCl is a strong acid. So which one wins? The strong one. So the solution is acidic. NH4F. NH4F divided NH4OH, weak, and this is HF. HF is weak, you don't see it here, weak. So when you have weak acid and weak base, then you need to have the values for Kb and Ka to compare them. For example, if Ka for Ka for NH4 is 5.6 times 10 to negative 10, and for Kb for F, negative is 1.5 times 10 to negative 11. Which one is larger? I'm sure you say the one that has a larger exponent, bigger. So this is NH4, so this is acidic. NH4 makes a, anyway, just to keep in mind that you need, when you end up having weak acid and weak base, then you need to have K values. Let's work on another question. It's a good question. As far as understanding the concept is a good one. It's slide number 52. And ammonium nitrate, NH4, NO3. is administered as intravenous solution to patients whose blood pH has deviated from normal value of 7.40. Would this substrate be used for acidosis when the pH drops below 7.40, or alkalosis, which is higher than 7.40? So again, let's see. NH4 OH, that's positive, that's negative, right? And this is a weak base. HNO3, this is a strong acid. So which one wins? The acid. So the solution is acidic. When you have an acidic solution, you perform it on alkalosis. When the pH is higher than 7.40. One more thing I want to tell you is just to give you the final equation so you won't be confused, is that the ratio between Ka and Kb seems like Ka is Kw divided by Kb. Remember, Kw at 25 degrees Celsius was 10 to negative 14. Whichever number is given to you as far as Kw, you divide it by Kb, so you will have Ka, and the same thing, Kb is Kw over Ka. So that's the relation between Ka and Kb. So if one of them is given, you're asked for the other one, or you need to use the other one, don't panic. You just need to plug it into this formula. This formula will be given. So the example is on slide number 56. What is Kb for fluoride ion when you have Ka? Ka for HF is 6.8 times 10 to negative 4. So F plus H2O gives HF plus OH. So you are given Ka and you're asked for Kb. Just go with the formula you just learned. Kw over Ka. Alright? Then you have Kw is, you need to know this, divided by 6.8 times 10 to negative 4, then Kb is going to be 1.5 times 2 negative 5. Okay. Then the next example, let's see what we have here on slide number 58. Slide number 58. Household bleach is a 5% solution of sodium hypochlorite. This corresponds to a molar concentration of about 0.70 NaClO, 0.70 molar. What is OH, concentration of OH, and the pH of the solution? For HClO, Ka is given as 3.5 times 10 to negative 8. So when you have NaClO, you add it to water as usual. So you can, on the PowerPoint slides, you see that ClO negative, right? Because you don't need the positive Na. That's why, that's the same, NaClO. but because we don't want you to be confused and you just need the anion, so why don't you eliminate the Na? And then you have HClO plus OH is left, right? So go ahead again, 0 and 0, that's ice table. Minus X plus X plus X, X and X and X, 0.70. So now you have what? You have, this is the KB, this is the base, because here you have the base, right? But you have Ka given for the reverse reaction. So it means first you need to find Kb. Kb, because this that you write is Kb, x squared divided by 0.70 minus x. You don't have Kb, so go ahead and find Kb from Ka. Okay, then you will find Kb 2.9 times 10 to negative 7. 2.9 times 10 to negative 7. So 2.9 times 10 to negative 7 is going to be x squared minus 0.70 minus x. Then try that assumption, 0.70 divided by kb. So you can calculate x without going through a quadratic equation. So x, which is the concentration of OH, is going to be 4.5 times 10 to negative 4 molar. And then you're supposed to find the pH, right? So go ahead and find the POH minus log of 4.5 times 10 to negative 4, which is going to be 3.35. Then pH is going to be 14 minus 3.35, which is going to be 10.65. All right, we still have a little bit more left, common ion effect and talking about acid-base titration, and a little bit more about the buffers, effect of buffers.